Hello everyone, this is Engineer Sanaullah Khan and today I am going to present about my final year project. The title for my final year project is Design and Prototype of SVC for Power Vector Improvement. Our group consists of two members including me, Mr. Sanaullah, and my group member Abraham Ahmed Razaki. This project is supervised by Engineer Shoaib Ahmed Sheikh, and the co-supervisor for our project was Fawad Ahmed Sheikh. So let's talk about the contents of our today's presentation. First, we will be introducing our static war compensator. Then we will be talking about literature review, problem statement, aims and objectives, block diagram, methodology and implementation, results, PCB design, enclosure design, final testing, future recommendations, and references. So let's first introduce the static war compensator. So actually the static war compensator is an electrical device used for compensating reactive power in power systems. It provides fast-acting reactive power compensation by using the solid-state components such as thyristors, capacitors, and inductors. Unlike the other devices that use the moving components, so that's why their response is low. But the SVC using the solid-state devices is fast, its response is very fast, and it has low losses and very low delay. They are capable of regulating voltage, improving the power factor, and enhancing the stability of an electrical network. They are widely used in industries, utilities, and renewable energy systems to optimize the performance and reliability of the power systems. Here you can see that this is the basic electrical network diagram of static war compensator. This line actually shows a transmission line, which is delivering power to the load, or we can say it's a bus. And in its parallel, we have connected our shunt device, the static power compensator. So what it does, whenever we need lagging wars or leading wars, we can provide both of them through these capacitor banks and through this controlled reactor. If the load is an inductive load, in that case, we will provide the leading wars to this line to improve the power factor or to stabilize the voltages. While in case of the penalty effect or in case of the capacitive loads, we can provide the lagging wars through this control reactor. So, and on the other side, if you look at the other side of the picture, you can see that this is a grid level static power compensator, which is a huge device and it's connected at the grid level. So the literature review. Before designing our project, we have gone through many papers and many research articles. Some of them are mentioned here. So the first paper that we have gone through is, Design and Implementation of Static Power Compensator for Power Factor Correction. In this paper, they have worked on reducing the power losses and the voltage stability. The other paper is the application of static power compensator for power factor correction and voltage regulation. In this paper, they have worked, basically, they have designed an effective filter to remove the harmonic distortion or to remove the THD so that it will increase or it will lead to the efficiency of the system and also the improved stability of the system. While the third paper that we have gone through is the power factor correction and reactive power compensation using SVCs. In this paper, they have actually designed static power compensator at the grid level and at high voltages. So they have actually worked at the grid level. So what is our problem statement? basically we have narrowed down and focused our research on the power factor. If the power factor is low, then the following problems may occur. The first one is that the useful power, that is the active power, will be lost because our system will be producing too much losses. That's why the actual power that is going to the load, that will be very low. The second one is the consumer has to pay penalty because of high reactive power in the system. The consumer has to pay the penalty in his bill due to high reactive power in his system are consuming by the load side. The third effect, the third worst effect that will be leading to this is the generation side. At the generation side, the generator will be facing high loading or overloading, and it will be producing high liability due to the high reactive power demand, and it will demand more current in the system. This diagram actually shows when we are supplying power to the load, then we are supplying both the active power and the reactive power. The reactive power is not of any use, and it is wasted. So this diagram shows that it is of no use. So we have to remove, or we have to absorb this power to improve our power factor and to stabilize our power system, and also reduce the losses in our system. Aims and objectives. So our aim for this project was to design a prototype of static power compensator for the power factor improvement. This design will involve selecting appropriate components such as capacitors and inductors. The control system for SVC will also be designed to regulate the reactive power and maintain the desired power factor. By using this device, it will regulate the reactive power. It can help to maintain a high power factor, reduce the energy consumption, and increase the capacity of the system. So this is the block diagram of our designed or our proposed SVC. So from the line, we are using the first step, we will be using a step-down transformer that will reduce the high voltages to low voltages. Step down the high voltages to low voltages. And then in our system, there will be either inductive load or capacitive load. So these low voltages will be applied to the zero crossing detection to detect the zero crossing. After the zero crossing is detected, the signal will be sent to the Arduino. The Arduino will sense this signal and taking it as a reference, and it will generate a pulse. That pulse will be acting as an input to the thyristor gate. At that instant, whenever we supply a gate pulse to the thyristor gate, at that instant of time, the thyristor will be on, and it will switch either the inductive bank or the capacitive bank, depending upon the reactive power demand. And there will be LCD as well that will show the reactive power, either we are supplying or we are absorbing, as well as the system voltages, either it is going to be high or it's going to be low, or it will be at constant level. So the first thing in our methodology and implementation that we done was the software implementation. So this is the proposed control circuit design in Proteus software. As I have labeled in this circuit diagram, the zero crossing detection is at this part. This part of the circuit is working for zero crossing detection. Whenever the zero crossing is detected, it will send this signal to the digital pin of the Arduino. The Arduino will sense this signal and it will generate a pulse and to this optocoupler. As the optocoupler is on, it will generate a gate pulse for the gate of the track. The track will be on at the instant of time. So our load or our inductor or capacitor will be switched on at that instant of time. So this is how this circuit is working. This is a very simple circuit, and actually we also have programmed this Arduino according to our need. And at this side, you can see a potentiometer that will be using to generate a delay in our alpha angle. Whatever the amount of delay we need, or at what instant of time we will want to switch on our load, it will be controlled through this potentiometer. These are the simulation results that we have run in the Proteus software. This is our input signal, that is sinusoidal signal. So whenever this signal goes to zero reference, at that instant of time, our zero crossing detection circuit will detect a zero crossing, as it can be seen that in every cycle there are 2 times the zero crossing is detected. And when the zero crossing is detected, the Arduino will generate a pulse, and at that instant of time, our load will be on. This is actually a triac conduction at an alpha angle. After going through the simulation phase, we have moved towards the low voltage testing at the breadboard. Using the NI Elvis kit that is at the Sector IB University lab. As after the successful simulation results, we have gone through the low voltage testing actually at 10 voltages. So this is the circuit diagram that we have designed, and this is our Arduino, and these all are our circuit components. After running this circuit and supplying the voltages to the circuit, the following results have been achieved, which we have been shown in this hardware testing video. Let's see how our output is coming. As you can see, we are using a potentiometer to control the output voltages. As you can see, as this potentiometer is moved, the voltages either increases or decreases, as you can see in this oscilloscope. This is how this circuit is tested successfully. After going through the low voltage testing, we decided to move toward to design the SVC, to design the PCB circuit for our proposed circuit. As we were satisfied with our results, so we gone through the PCB design. So this is the PCB circuit diagram for potentiometer PCB, zero detection PCB, and a triac control PCB. They have been designed in Eagle software, and we have designed it separately so that we can easily find out the problem that is occurring in this circuit. So it will be flexible too. These are the printed PCB designs: the zero crossing detection circuit, the triac control circuit PCB, the potentiometer PCB, along with the soldering. These have been printed at the Fab Lab of Sakkara University at very low and effective cost. The third and the next part was to test the same prototype at high voltage. So this is the circuit diagram of our SVC, and these are the PCB. And this is the transformer. After testing it at high voltage, almost 90 voltage, we have achieved the following results, as it can be shown in this video. As you can see that by varying the potentiometer, the output voltage is controlled, and either increases or decreases, and we can easily control it. And this test was also successfully done. After testing at high voltages, then we decided to go for the enclosure design. This was also an important part of our final year project to design the enclosure for our prototype. So we designed our enclosure in the SolidWorks and using the laser cutting tool that needs the two-dimensional design. So we designed it in our SolidWorks software. So these are the side views of our two-dimensional designs for our enclosure. This is the front view and this is the back view. After the laser cutting tool that is used at the Fab Lab of Sakurai Bay University, the final prototype, the design was looking like this. This is the 3D front view. This is the 3D front side view, and this is the 3D side view. After all the things were ready, we went through the final hardware testing. So this is the actual setup for our proposed SVC. This is the hardware setup, and this is the inductor. This is our designed SVC device. This is the capacitor, power supply, the power factor meter, again the power factor meter. This is our load, and this is the oscilloscope to show to view the output voltages. After testing it successfully, we have achieved the following results. As you can see that we have applied the 90 voltages, and this column shows the output voltages. At the start is you can see that our inductor was switched on. So it was decreasing the power factor, and that's why due to this the output voltage is very low. As we switch off more and more inductor, we can see that our power factor starts to improve as it can be shown in this column. At the start it is 0.34, and then it boosts up, and finally it reaches to 0.935. At this stage, both the capacitive wires and the reactive wires are balancing out each other, so that's why we are achieving the high power factor. After the balancing stage tilts down, then our capacitor provides the leading wires to the system, so that's why the power factor is increased, and then it starts to decrease. This is the output voltage at the versus inductor voltage, input voltage versus inductor voltage. This is the waveform at 0 angle, and after varying the alpha angle, that is at 27.36 degree firing angle, the output voltage looks like this, and when we further increase our alpha angle, firing angle, then the output voltage is looking like this. So this is the firing angle versus reactive power relationship. As you can see that at the start, at 0 power factor, at 0 firing angle, our reactive power is very low, is very high. As soon as we increasing the firing angle, our reactive power is decreasing, and finally it is generating the lagging wires, and then it starts to generate the leading wires. As you can see, the negative sign shows. Then the next relationship we have between the firing angle versus load voltage. As you can see at the start, the SVC firing angle, it is at 0 degree. The voltages are low because at this instant of time, the inductor is fully switched on. And as we start decreasing to switch off the inductor, our voltages start to improve, as it can be seen in this whole line. This whole line shows that how the output voltage is increasing by increasing the firing angle. The last one is the relationship between firing angle and the power factor. As I have already told that as we increase the firing angle, at some stage our power factor will be very highly improved, and then it will start to decrease because of the switching of the capacitive bands. At the start, the power factor is very low because of high reactive lagging wars generated by the inductor. As we increase our firing angle and start switching off the inductor bank, then our power factor starts to improve. At this stage of time, both the capacitor and inductor cancel out each other, so our power factor is very high at this point of time. After this point, the capacitor starts to dominate and over the inductors. So our power factor starts again to decrease, and it goes slowly, it decreases down again. This is how the firing angle versus power factor relationship graph shows. So the future recommendation for our project is that how we can further work in this project. We can further work on the control strategy of optimization. We can improve its control strategy as we are manually controlling it. It can be controlled automatically or dynamically by using different control strategies like fuzzy control logic, PI controller, or other very high efficient controlling devices. This device can also be used for fault detection and protection in the power system in future. As well as in future, we can extend it to multi-level static war compensator so that more and more wars can be generated and it will be provided to the transmission line. And the last point is that we can generate real-time monitoring and control of our SVC device by making it more efficient, more reliable, and it can be used with the modern technologies. By implementing the modern technology with it, we can have the real-time monitoring and control of our power system. So these are the future work that can be done in our design project. These are some of the references that we have gone through while designing this project. Some of them are from the year 2019, and some of them are from the year 2021, and again 2020. So thank you for listening. Be careful. Thank you.